So for the first question you have on this practice test, you're asked to show or rewrite the sets in set builder notation. Set builder notation is basically a notation where you're given a formula to reproduce the list that's in front of you. Now, as we look at the first one, set X, I can see a couple of things about it. I can see that, each time that we're jumping +3. So all these are going to be multiples of 3, and I am giving an indication right here that this set does go on forever and ever and ever. And when we do set builder notation, we tend to make use of the natural numbers, which is usually signified with a fancy looking n like that. And sometimes we use, as far as a variable goes, we use the letter n, lowercase n, to represent a member of the natural numbers. So when we start making the formula for this, we always start with x equals the bracket, and we just say that x, capital X, is equal to lowercase x, such that lowercase x equals 3 times n, and n is an element of the natural numbers. The natural numbers start with 1, and they're your counting numbers, 1, 2, 3, 4, 5. They're basically integers, excluding 0 and negative. So, as we reproduce this list, this is 3 times 1, this is 3 times 2, this is 3 times 3, so forth and so on. So that's where it comes from. And we always try to interject the natural numbers if and all we can find it. So when we look at this one here, some differences about this one. First of all, it starts with 12 and goes down in value. So that that could cause its own issue. But it does go down each time by 5. So there is some sort of constant difference along the way. So there is a way to interject the natural numbers in there. I also see that I don't have the symbol indicating this goes on forever and ever. So this is a finite set, so I have to limit it, to natural numbers that are between other numbers. So I'm going to start with the fact that, y equals lowercase y, such that y equals. Now I need to come up with some sort of formula where I can come up with an idea of what's going on with this. So my first number is 12. But, I like to have some number, which I'm just going to call y right now, the first y value. And I know I'm going down by 5 each time, so minus 5 to the n, which in this case, for our first term, should equal 1. So the first term should basically be equal to 17, because, this would be y1 equal, minus 5 for the first term. And so if I add 5 to both sides of that, the first term is 17. So it's 17 minus 5n, where n is a natural number. And so here n equals 1, 2, 3, 4, 5, 6 terms. So I could either say that n is less than or equal to 6. I could also say that n is less than 7. So there's different variations you can do for this type of problem. So those are two instances of set builder notation for these two sets up here. Moving on to number 2, we have the exact opposite. Now we're given the set and set builder notation. What we want to do is write the list in roster notation. And again, we're going to use if it's a set that's supposed to be infinite, we're going to use the symbols to indicate it goes on forever. If it's a finite set, we're just going to write out the entire list. If it's a long list, you could sometimes use the same symbol, those 3 dots, and basically, put them in between. As long as you can show enough that there's a pattern occurring, you can shorten the list like that and make your life a little easier. But for the first one, m equals x is such that x equals 2n minus 4, where n is a natural number. So as I look at this in roster notation, this is going to be, well, the first number I would put in here is 1 for n. That's the first natural number. So 2 times 1 is 2 minus 4 is negative 2. Then if I let n be 2, 2 times n is 2 times 2 is 4, minus 4 is 0. If I let n be 3, 2 times 3 is 6, minus 4 is 2. And as you can see, it's producing this set of numbers, basically multiples of 2, starting with negative 2. So each time I go from one number to the next in my list, I am moving up by 2 units. This one goes on forever since I don't have a limit to what n could be. Like up here, n is just the natural number. Down here, as we're going to see momentarily, n has a limitation. It has to be less than or equal to 7. So I am going to use the symbols that indicate that this would go on forever, and that would be this one in roster notation. For Q, same sort of deal here. We're going to start with the first natural number 1. So it says Q is made up of values of x, such that x equals n squared, where n is a natural number and it's less than or equal to 7. So the first number we would use is 1. 1 squared is 1. The next one would be 2, so 2 squared is 4. And so this would produce your perfect squares up to 7 squared. So I would just have to continue this list. Until I end up with 7 squared, which is 49, and then I get to end my list. I don't have to put the symbols indicating it keeps going, because it doesn't. It's a finite list for this. So you have to be sure that you know the difference between a finite list and an infinite list when you look at the notations. So moving on to the next problem. So some set notation problems here. You're given a universal set, which is the integers from 1 to 15. And then you have v, x, y, and z, which are all subsets of them. They contain some, but not all the numbers. Some of them may contain the same numbers, like for instance, v and y, they share 5, which seems to be the only one they share. And so you're asked these various things down here and make sure you know the various notations. So for A, I want to find the intersection between x and z, which means, I'm looking at right now these two, x and z, and I'm looking for the intersection. The intersection means I'm looking for values that are in both of those sets. And so when I look at this, x and z, the first number I see in x is 2. Z does not have 2 in it, so that one's not going to be an intersection. X has 3 in it, but z doesn't, so that's not going to be one of them. They both have 4, so it's going to be one of them. Z has 5, but x doesn't. They both have 6. They're both missing 7 and 8, so they're not a member of either set, so it's not going to be in there. They both have 9. They don't have 10. X has 11. Z doesn't. Z has 12. X doesn't, so those aren't going to be included. They are both missing 13. They both have 14. And they're both missing 15. So the entire set of the intersection of x and z is 4, 6, 9, and 14. For B, now this one is this is the union of v and y. So when I look back to these, I'm looking for elements that are in v or y or both. So when I start the list, I look in v, it has 1. Y doesn't, but since it's in v, I will include it. It's a union. Y has 3, v doesn't. So it's gonna be included because it is in Y. Now 2 is not a member of either one of them, so 2 is not included. Um, as I can see, the next number up on the list of both of them is 5, so they both have it, so 5 is included. 6, 7, 10, 11 are in Y but not V. But since it's a union, that's good enough. So 6, 7, 10, 11. Y has 13. Well, V has 12. Y doesn't, but since it's in V, it's going to be included. And Y has 13. Even though V does it, all it has to do is be in one of them. And there's the list of numbers that, or the set that would be the union between V and Y. For the next one, let me move this over a little bit. And you might not be able to see all the numbers up here, but I'm going to keep going with it because you can see it on the paper. So X and not Y. So I'm going to rewrite the list X. Maybe use a different color. Use orange. So X, if we go through and list what X was again. And we're doing an intersection. Now this means, the things that are not in Y. So I would look at the list of Y, what's in Y, and anything that's not in that list but is in the universal set U, that's what I would include. So now it's an intersection, so now I'm looking for those values that are in both of these sets I've written in roster notation. And so what I'm really only looking for here are the numbers that are in both. So they both share 2. They both share 4. They both share 9. And they both share 14. And so the final answer for this is going to be 2, 4, 9, and 14. And that would be the intersection of X and not Y. Now as far as different notations go, let me erase that real quick. And the same thing as Z and not V. And I do show this, and I do talk about this in the work that you do in this section, so in that unit. So these would be the same thing. So when I start with Z, and I'm subtracting anything that might be in set V, which is 1, 5, and 12. Now with sets, I mean, because Z doesn't contain 1, if I'm getting rid of 1, well, I don't have it to get rid of, so it isn't like any kind of negative occurs or anything. So, the 1 doesn't really affect me in anything for V. The fact of the matter is now, when I go to do, the other ones, 5 is in Z, and since it's in V, I want to get rid of it. And same thing with 12. 12 is in V, so I would get rid of it. So the final answer for this would be 4, 6, 9, and 14. Now this is indicating here a multiplication between sets. And what that means is that the answer to this, just use this, is going to basically be the set of all possible ordered pairs where I take a member from the set X, a member from the set Z, and I make ordered pairs out of them. That's what the multiplication indicates with this. It's a cross multiplication, which means this would be quite an extensive list for X and Z, because I'd have to go to each number in X and pair it with a member of Z. So for instance, just to start it off, I'm not going to necessarily write the entire, well, I'll write out the entire list. And so that is the entire list of ordered pairs that would come from of cross multiplication between sets X and Z. So, probably on the test, if you were given any cross multiplication, it wouldn't be sets that are quite so big. It just happened to work this way on the practice test for this, that I made one and didn't pay attention to see how big that was. So you wouldn't necessarily have to worry about this one as being as much of an issue. So for the next one, the other two are much shorter in the long run. So let's get into those. So again, for this one here, you have to pay attention that the set notations do have an order of operations. So, so I'm going to, start off dealing with what's inside the parentheses. And I'm eventually going to do that union, and then I'm going to have anything that's not in that union. So that's what's going on with this. So I'm going to do this in stages. So the union on the inside is going to be anything that's in one or the other or both. So that's a member of anything that's in the union of not X or Z. And now I want to do, anything that's not in that set. I want to take care of this, apostrophe out here, which means now I'm going to go to the universal set and choose only those numbers that are not in this list here. So what I'm looking at for a final answer is the number 2, 3, 4, 5, 6, 7, 8, 9, 10 are all in there. 11 is not. 12, 13, 14, and 15 are all in there, and that's as far as the universal set goes. So this set is just the numbers 2, 3, and 11. So this one here, again, I'm going to have a number of work to do. X naught again, which we had from the previous one, is going to be, so that's X naught, union of Y. I'm going to do that union, intersected with what's going on in this parenthesis, and I might want to move over a little bit more on my canvas here. Not Z would be anything that's in the universal set, but it's not in Z. So, and that's going to be unioned with set V, which is a small one, thank goodness. So sometimes when you have multiple operations on any set, there's going to be a good bit of writing involved, and that's going to probably take the longest period of time. It isn't difficult computations, just knowing what the symbols are. So I'm going to do the two unions first and then do the intersection. So the union in here, again, anything that's in one or both sets, I'm going to have intersected with the union between these two sets. And so now I just have to do the intersection between these two sets. Now the intersection are only those that are contained in both sets. So let me go to a different color for this. I'll just go to blue and indicate, okay, well, when I look at the two sets, they both share 1. They both share 3. They both share 5. They both share 7 and 8 and 10 and 11, 12, 13, and 15. So they're pretty close to being exactly the same sets. Really, the only thing they don't have in common is one has 2 while the other one doesn't, and the other one has 6 while the other one doesn't. So the final answer is going to be the set And so that's the end of problem number 3. So not, they could be lengthy in a little bit because of the fact that you have to go through and make sure that you're keeping the set straight, you know what the symbols mean, but other than that, not too bad. Moving on to the next problem. So for this, you're asked to create a truth table for each of the following. So I'm going to do just that. So this one here only has P and Q as the primary variables. Yeesh, it's a little bit too big. So I'm going to have P and Q starting off my truth table. And of course, all the possible combinations of true and false statements between P and Q alone are represented here. So I start with those. Now it looks as though another one I have to consider is not Q. I don't really have to worry about not P or anything like that. I just have to have not Q in there. So not Q. Is this going to be anything that's the opposite of Q? So this is false, this is true, this is false, this is true. And so now I can actually get into what I see up here. So if I have, okay, P and not Q. So I'm looking at this one and this one right now. The other way for that to be true is for both of those columns to have a truth value in there. So this would be false, this would be true, and the rest would be false because they have at least one false in them. Whereas when I look at now, erase these, Q, if and only if P, so biconditional. So I'm still looking at these two, and the only way for that to be a true statement is for P and Q to have the same truth value. So either they both have to be true or they both have to be false. So this would be true, this would be false, this would be false, and this would be true. And so I have those two, and now I want to do the final one, which deals with the conditional statement. If P and not Q, then Q if and only if P is true. And so when I look at this, now I'm only looking really at the conditional statement. So I'm looking at these two columns at this point. And for this statement to be true, either, if the first one is true, then the second one has to be true. Or if the first one's false, it's automatically true. So in these two, in this one, and this one, since this statement here is false, it's automatically this is a true statement. And this one here, it's true, but it leads to a false statement, so this would be false. So basically, the statement we have in A would be true if P and Q are both true, if P is true and Q is false. No, take that back. If P is false and Q is either true or false. And it would be a false statement if P is true and Q is false. So, that's the truth table for this one. For the next one, there's 3 variables involved, P, Q, and R, so it makes it a little bit longer of a setup. And so I start off with my 3 variables, P, Q, and R. So that's every possibility of P, Q, and R in combination with each other. The next thing I want to look at is, okay, well, let's look at this statement here. If P, then Q. If P then Q, it means that if P is true, Q also has to be true. That would make it a true statement. Or if P is false, it's a true statement. So I look at these two columns here and here. P and Q are both true. That's a true statement. Same thing with this one. For the next two, P is true and Q is false. So these would be false. For the next four, since P starts off as false, these statements would be true. So I have that. And there's different ways to construct these tables. Sometimes you'll see the textbook, they'll just like, put this statement in here, P, if P then Q or R, and, just kind of like, indicate them and put little numbers underneath them. But just always make sure that you are indicating what the final answer is, because ultimately we're looking for the truth table for this. So when I get to that statement, if P then Q or R, we're looking at this column and we're looking at this column. For the statement to be true, that's in red, either the column in green has to be true, the column for R has to be true, or both have to be true. So since I have these two columns being true, for the first one, that's true. Same thing with this one. Here they're both false, so it's false. Here, same thing. Both false. Take that back. I was looking at the wrong thing. R is true and F is false. That still makes this a true statement. Here, they're both false. R is false. If P then Q is false, so this is a false statement. And for the rest of them, I either see one or two true statements, so the rest are true. So basically, this statement here would only be false under the condition where P is true and both Q and R are false. The statement would be true otherwise. So it's almost a tautology. The only thing that's keeping it is this one false over here. So those are those two examples. For number 5, you're asked to write a converse, inverse, and contrapositive of the statement. If it is summer, then it is hot. So for this one here, the converse merely switches the if and then portion. So, we're looking like, the it is summer, it is hot. So, so now for the converse, I'm going to have if it is hot, then it is summer. Now, we're not stating the truthfulness or falseness of the statement. We're just basically, stating an if and then statement here. For the next one, the inverse, we have an inverse if we negate the if and then statements. So what's going to be happening for the inverse, back to the original statement, if it is not hot, or take that back, not summer, because that's what the original statement was, it had summer first. If it is not summer, then it is not hot. So basically the inverse is just negating the if and then portions of the original statement. The last one we talk about is the contrapositive. The contrapositive is like, it's kind of like combining the converse and inverse together. I mean, you can look at it as me either negating the converse or me doing a converse of the inverse, switching the if and then portions of the inverse, whichever way you want to look at it. So basically, this one is if it is not hot, then it is not summer. And so those are examples of those three things. Now getting back to some truth table things and determining the truthfulness or falseness of statements, 6 is slightly easier because it's not asking you to come up with an entire truth table. It's only asking you to come up with instances where A and B are true and C is false. And so that's the premise I'm going to work under for both of these. So I really don't care what goes on with the other instances. Just going to list A, B, and C. And so I want what's going on when this is the case. And I'm only working with that one case. So it's a little bit less work than we had to do for creating an entire truth table. So in A, I want to look at, okay, well, let's look at A and B. For A and B to be true, both A and B together have to be true at the same time, which is the case. So we have this. Now under the next parenthesis, I'm going to look under, okay, if C, then B. The only way for this to be true is if C is true and B is also true, or if C is just false. C happens to be false, so this is a true statement. And so if I go back to the overall statement, A and B, if and only if C then B, that's how you read it in English. The only way for this overall statement to be true is if this and this have the same truth value at the same time, whether it's both true or both false. I have an instance where they're both true. So this would be true. Scooch this over a little bit. And plus I have a part C over there. For this one here, C and A. Again, for this to be a true statement, both C and A have to be true at the same time, which is not the case. A is true and C is false. So this is a false statement. B or C, for that to be true, either B or C or both have to be true. And since I have B being true and C being false, this is a true statement. So I have the two groups now done. Now I want the overall statement. If C and A are true, then B or C is true. So I'm looking at these two columns here. Again, for a conditional statement to be true, either the left-hand side has to be true and the right-hand side has to be true at the same time, or the left-hand side just has to be false. And the second condition is what I have. This is a false, so this is automatically true by default. For part C, again, I'm going to start with the same premise. A, B, and C, true, true, false. I have some preliminary things I have to look at. Not A is going to come into play. So not A is going to be false. And not B is going to come into play. That's also false. And again, I'm going to move this over a little bit more. Maybe expand that a little bit. All right. So the next statements, I'm going to look at the two quantities now. I have C and not A. So I'm looking at this and this here. For that to be a true statement, both of these would have to be true. Well, the fact is both of them are false, so this is automatically going to be false. And then when I look under B, not B or C, I'm looking now at these two, not B and C. For that to be true, one of those has to be, true. In this case here, C is false, not B is false, so this is false. So now I'm going to come down to the very last statement. So I'm kind of showing how you build on the statement. That's why I like doing it this way instead of like kind of putting things underneath the symbols individually, which is sometimes how the book sometimes shows it, because it lets you see how you had to build up to get to this point. So now I'm actually able to make the final statement. It's an if-then statement. So if C and not A is true, then not B or C is true. Again, for this statement to be true, either the left and right hand side of this statement in red has to be true at the same time, or the left hand side just has to be false. And that's what's going on here. The left hand side is false, so that automatically makes this a true statement. And so these are basically instances where you have like kind of mini truth tables, and you just have to do it for one case. So but again, the work you would show for stuff like this would basically be instances where you're just doing one case. For number 7, you've seen problems like this in two different situations. One was when you're just doing counting. You wanted to count, and using Venn diagrams and whatnot. Another instance we do is doing probabilities. So questions about both can be used, and we should certainly explore both of them. So what I'm going to show on this one is, first of all, I do need to, essentially, get some information together to help me, answer these questions a lot easily. So the thing I have to look at is, since I have like, coffee, tea, and soda preferences, I do see that there's some that like 2 of the 3 or all 3. There's overlap between here. So that 180 that like coffee includes the 18 that like all 3 options. It includes the 40 that, like coffee and tea. So I have to be sure that, I'm accounting for these. So in order to make sure I'm counting for them properly, I'm going to create a Venn diagram. And so I have my entire population. So everything that's within the rectangle should add up to 300. And I have 3 circles. I have those that like coffee. I'm just going to say that's C. I have those that like tea. And since I do have those that like both, I know they do overlap. And I have those that like soda. And I know there's overlaps. And there's actually an overlap where, all 3 are preferred. And so, I know I'm going to have a Venn diagram that overlaps just like that. Now I got to get the numbers filled in properly. And it's best to kind of start off with the most restricted first. I have 18 that like all 3. So I know there's 18 people in this group right here. Now if I go up the list, there's 31 that like tea and soda. So that's this overlap, between the green and blue circles. I don't really care about the red, but I have to keep an idea that 18 are also in that coffee group. So there's going to be some that also like coffee, but there's going to be those that also do not like coffee. And, so 13 are going to like the tea and soda, but not prefer the coffee. 28 like coffee and soda. So I'm looking at combinations of the red and blue circles here. Again, of that 28, 18 do like tea as well. That means that, 10 don't like tea, but do like the coffee and soda. And same thing with, going up the list, 40 like coffee and tea. That's a combination of the red and green circles. But again, 18 of those are those that like all three. So those that only like two of them, the coffee and tea, would be 22. Because I have to make sure that the overlap between the green and red circle totals 40, but some of that also includes an overlap with the blue circle as well. So, and now I work my way out. So now I have so going back to the coffee, I have 100 people that like coffee. Those that are in the red circle that I've already accounted for add up to 50. So there's 130 that just like coffee. They don't like tea. They don't like soda. And likewise, 80 that like tea. We have 22, 18, and 13 that we've already accounted for, which gives us 27 out here that just like tea. And similarly, for 70 that like soda, since we have 10, 18, and 13 in here, we have 29 out here that just like soda. And so, like, if I add up all the numbers I see in the red circle, they should total 180. If I add up all the ones in the green circle, they should total 80. If I add all of those in the blue circle, they should total 70. And if I add all those together, and all these numbers I have up there, that's 249, which means there's 51 that don't like either of these options as their drinking preference. And so, that's often, sometimes that's a question that's asked of you, but it's also something to keep in mind because as we go through this now, we have to consider this. So, how many people don't like any of the three preferences listed? Well, that was easy because we came up with that from, just like filling in, making sure we had everything accounted for in this. That's 51. How many people like only tea? And so when I look at only tea, that's the 27 that don't fall into the red circle or blue circle either. So there's 27 that only like tea. And so once you have the Venn diagram, it makes answering some of these much, much easier. How many people like coffee and soda, but not tea? So, I'm looking at, the intersection between the blue and the red circles. I have 28 people that fall into that category, but there are 18 of them that like tea. So only the 10 I have in there just like coffee and soda, but they don't like tea. So 10 there. I can also answer these probability questions that you're asked with the same information. Now that I have the coffee, tea, soda, and everything preference in there, I have to keep in mind, though, that if we're choosing people, and since we're not told otherwise, we're assuming there's no replacement. Usually for you to assume that there is replacement, you have to be told that there is replacement. So if one person from this survey were chosen at random, what is the probability that the chosen person does not like to drink coffee? And so, I could go back to the list. I know there was 180 people that like coffee. So, I know that there's, in this case here, it's only one person, so this makes it a little easier. There's 120 people that don't like coffee out of 300. And you can reduce that. I mean, you could say it's, 12 out of 30. Um, you know, essentially 6 out of 15 if you simplify it to lowest terms. If you have it as a decimal, it is, actually I think it goes further, 3/10, or no, 2/5, which also boils down to 0.4. So if I was doing this as a percentage, I would say 40% of the people, do not like drinking coffee out of this group. Now here we're picking 3 people. And we want to see what is the probability that at least one likes to drink soda. At least one is an easy situation to take care of if you take care of it correctly. Theoretically, if I wanted to see the probability of at least one liking to drink soda, I'd have to do okay, the probability that one person likes soda, probability that 2 people like soda, and the probability that 3 people like soda, and add them together. That can be quite a bit of work, especially with overlapping sets and things like that. So, what I have to then do is, do a lot of various combinations. this one is much easier if I realize that the probability of at least one liking soda is the opposite, and therefore 1 minus the probability that none like soda. Because the probability that none like soda is really easy to compute. Because I do know that I have, going back to the information we had from the problem, there are 70 that like soda, which means there's 230 that don't. They don't like soda. I mean, may like other preferences. They may not like any of the preferences, but they do. I do know that basically 230 don't. Um, Now I can take care of this using combinations, or I'm going to do this pretty simply. The probability that the first person does not like soda would be 230 over 300. And the next person would be 229 out of 299. And the next person would be 228 out of 298. So it's the probability the first person doesn't like it, the probability the next person doesn't like it, given that the first person was already chosen and didn't like it, so forth and so on. You can use the combination method, which certainly, if it's much more to it, like F is going to be, then I would certainly use that. But this works out to be the same thing. In the end, it comes out to be about 0.5507. So if you're picking 3 people from random from this study, you have a little bit over a 55% chance of picking somebody who does like at least one of them liking soda. So go a different color for the next one. If 5 people from this survey were chosen, it was a probability that 2 of them do not like to drink coffee, tea, or soda. Okay, so going back to this and the Venn diagram, and you have the Venn diagram hopefully in front of you now that hopefully you've drawn it. We have 51 that that do not like coffee, tea, or soda. I was going to abbreviate it, which means we have 200 or 249, yeah, that like at least one. So if they like at least one, they don't fall. So basically what I'm trying to do is figure out a way of making this into 2 different categories if I can, or, or making this distinctible categories. There's only really 2 here. There's those who don't like any of these, and there's those that like at least one or more of these things. And so, for this probability, because I want to see the probability of 2 of them, when I start getting to situations where I'm picking 5 people, or I'm picking a number of people, and I want to see like anything that's, you know, 2 or more, or just 2, it gets to be complicated to try to use a procedure much like this one up here, because then you have to think, okay, well, I have to figure out the probability of this certain instance, and I got to figure out how many ways that I could combine those instances together. It's a pain. Um, but for this, I could say, okay, well, the probability of 2, exactly 2, not liking soda would be obtained from me doing, well, I have 300 people and I'm picking 5. So the bottom number here is going to be the combination of C, or it's going to be the combination of me picking 5 people out of 300. But I have these two groups. I have the 51 I do not like and the 249 that like at least one. I want two of them from this group here, from the 51. So I'm going to have 51C2, which means I'm going to have three from the other group. So the other group, 249C3, there we go. And that's how I would set this up. I was able to make this into two distinct groups. How you go through it, you might be able to make more distinct groups and then say, okay, well, if I have two people from this group, then I would have like this many from this group, this many from this group, so forth and so on, depending on the situation. And so when I work these out, now some calculators can calculate these combinations, even scientific calculators. Kind of go through the work on this. 51C2 would be 51 factorial over 49 factorial times 2 factorial. (249C3) would be 249 factorial over 246 factorial times 3 factorial. And this comes from the formula that, NCR equals n factorial over n minus r factorial times r factorial. That's the formula for that. And that's what I'm doing. Here I have the n value on top of both of these. I have the subtraction of the two subscripts, factorial, and then I have the r value subscript. And the same thing for this one. I'm going to have 200 or 300 factorial over 5 factorial. Now I have to know what these factorials are, okay? 51 factorial would be 51 times 50 times 49 times 48 times 47. And the 49 factorial would be 49 times 48 times 40. So 49 factorial would cancel out most of 51 factorial, leaving only the 51 times the 50. 2 factorial is just 2. That's an easy one, 2 times 1. Same thing with the 249 factorial and the 246 factorial. 249 factorial would be basically 249 times 248 times 247 and then times 246 all the way down. Well, that 246 all the way down is 246 factorial. So this would have 249 times 248 times 247. 3 factorial, and that would cancel out the 246 down here. 3 factorial is just 6. Here I forgot to put the number down here, the 5 factorial. I should have the 295 factorial there. Because the 300 factorial would have 300 times 299 times 298 times 297 times 296, and then times everything that's in 295 factorial. So this would be 300 times 299 times 298. So even though you have some big numbers here, it isn't like you have to compute out what 51 factorial is or 300 factorial is. As a matter of fact, if you put some of these values into your calculator using the factorial symbol, because some of them do have it, you'd probably get error messages due to the fact that, that would be awfully hard to do. Now, 5 factorial is 5 times 4 times 3 times 2 times 1. So 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1. So you'd have this. And so it's much more doable with this. And if you work out these numbers and put them into the, right, dividing a fraction type thing, you're going to have the 51 times 50 times 249 times 248 times 247 times 120 over 300 times 299 times 298 times 297 times 296 times the 2 times the 6 for the two denominators up there. And if you work that out, simplify it, put in your calculator correctly, you would get about 0.1655. So basically, if you pick 5 people from this survey at random, you have about a 16.55% chance that exactly 2 of them will not like to drink coffee, tea, or soda. So in the involved problems, I mean, the calculations, you have to rely a lot on cancellation. As I said, there might be some calculators, scientific ones. If you have a graphing one, most of them will do the calculation for NCR and NPR. So that could be a shortcut as well. But if you have to do it more by hand, there's cancellation, which means you know how factorials do work. So make sure that you're up on that, depending on what kind of calculator you have available to you. Okay, so this one here, we're getting back to truth table things. Now, I mean, there's the various laws that you could also be aware of. The difficulty is some of those laws, seem very similar to each other, and sometimes students will mix up the statement of them. And if you state by this law, thinking that confusing one law for the next, you're going to be very wrong with that. And since those laws are all proven essentially by using truth tables anyway, I think it's just better to do situations like this by using a truth table. And so that's what I'm going to show here. The first thing I have to do is translate what's going on in these statements. So I like to make a symbolic logic statement and then use a truth table to figure out what's going on with that. So, if it does not rain today, then we will visit the amusement park. So, and I try to make sure I use symbols that are very similar. So I'm going to let R represent raining today, and basically we're saying it's not raining today. If that happens, then we'll go to the amusement park, which I'll let that be symbolized by A. So the first sentence is translated into this. If we visit the amusement park, we will ride the roller coaster. So again, visiting the amusement park is A. If that happens, then we will ride the roller coaster. I'm going to use C for coaster because we already have R for rain. So that takes care of the second statement. We did not ride the roller coaster. So we're being told in our third statement, this is in fact true. Therefore, it rained today. So we're going to say, therefore, oh, sorry, we did not ride the roller coaster. It's not C. Mix up my own symbols. Not C. Therefore, we're going to assume, okay, then R. You could also have said, essentially, another possible difference with this. I mean, there's different variations how you do it. I mean, I usually go sentence by sentence. But you could say, therefore, if not C, then R. So, I mean, either one of these would be acceptable and they would have the same result. So, I'm going to do this one, the first one I wrote. So now I'm going to set up a truth table with R, C, and A. So this represents every possible combination of truth and falseness between 3 variables. Because I'm going to be using the left-hand one primarily, I want to make, I mean, in either case, I'd have to know, what not R is and not C. And it's better to write them out instead of trying to do them in your head, because these are not really hard things to do, mind you, because this one's just doing the opposite of everything that's over here. So I'm going to have, false, 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 true, 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 true. This is going to be false, false, true, true, false, false, true, true. So, just having them out here so that, and when you write them this way, having them shown like this so you can show what it is you assume these were, lets me know, like, if you made a mistake because you just simply miswrote a truth statement and put a true where a false should have been, or if you misinterpreted the entire symbol. I mean, so those kind of things could be shown a lot easier if I see this kind of work. So now I want to do the first statement that actually would lead to my conclusions. Not R, if not R, then A. So I'm looking at this one here first and this one here second. And so for the first four statements, it's going to be true because not R is false. And for a conditional statement, if the if part is false, it's automatically a true statement. For the rest of them, not R is true. So the only way for this statement to be true is if A is also true. So for the fifth one, it's true. For the next one, it's false. And then true. And then false. The other statement, if A, then C. Now I'm looking at this statement first, and then this statement second. Again, if both A and C are true, it's true, so that's going to make this true. If A is false, it's automatically going to be true. If I have A being true and C being false, like in line 3, this is going to be false. A is false in line 4, so I don't really matter what C is. And then, they're both true. A is false. A is true, but C is false, which makes this false. And then A is false, which makes this true. And so when I look at my final statement, I'm going to see, like, I'm going to redo R over here just for the sake of having it over here. I'm only really concerned with, when I look at these three, because these are my three conditions, where all three of them are true. And there's only one instance where all three of them are true. I mean, the rest of them I could do the rest of the truth table for, but I really only concerned about this one here, line 4. In line 4, R is true. And since these three are true, and this is automatically true, and that's the only instance where all three could be true at the same time, and when all three are true at the same time, R is true in that instance, this is a true statement. It is a valid argument. So this argument is valid. So if it doesn't rain, then we visit the amusement park, and then if we visit the amusement park, we'll ride the roller coaster. If we did not ride the roller coaster, then it had to rain. If these are the conditions, and I'm accepting those first conditions to be true, that has to be the case. For the next one, B, if I drink too much diet soda, I get a headache. If I get a headache, then I cannot sleep. I did not drink too much diet soda, therefore I can sleep. So, let me translate these statements. I'm going to say D for drinking too much diet soda. If I drink too much diet soda, then I get a headache. If I get a headache, so if H, then I cannot sleep. So I'm going to say no S. The third thing that's being assumed as true, I did not drink too much diet soda, so not D. Therefore, I can sleep. So these are the statements being made. I'm assuming the first three to be true. I want to see if the first three being true makes the fourth one true automatically. So again, I'm going to have three variables here, D, H, and S. So I have every possible combination of the variables D, H, and S being true and false together. I'm going to look at these conditions because not S and not D play a role in this. So not D and not S are two things I want to also include on this, so I know what's going on with those. And again, they're easy enough. I'm just looking at D and just doing the opposite truth value. And the same thing when I do not S. I'm just going to do opposite truth values. So now I'm going to get to the actual statements that I have. Yeah, so the first statement says, okay, if D, then H. So I'm looking at this one first and this one second. Again, if they're both true, like in the first two cases, it's true. If I have D being true and H being false, it's false. In the remainder, I have D being false, which makes the conditional statement automatically true. So these are the instances of truth and such for if D, then H. The next one I want to look at is if H, then not S. So I'm looking at now this one first and this one second. So when I look at, the first instance, H is true, not S is false. Since H is true, the if part is true and the then part is false, this is a false statement. For the next one, line 2, they're both true, so this is true. For the next two, H is false. So that makes this conditional statement automatically true. And the same thing kind of works out for the rest of them. I have true then false, which makes it false. And the rest are going to be true statements. And I also have now not D, which I've already listed. I'm not going to list it again. I just want to keep track of instances where, now I want to find where all three of these statements, this one here, and this one here, were all true. So I have this line right here, this line right here, and this line right here. All three of those statements are true in the last three lines. So now I want to see what goes on with S again. Well, I can see right here, S is false here, true here, and false here. So I have instances where if all three are true and I end up having S being true, but I also have two instances where all three are true and S is false. Therefore, it only takes one of them to be have a false S for this. That's enough. This is not a valid argument. If these conditions are true, basically, if I drink too much, then I get a headache, and if I get a headache, then I cannot sleep. Even with those two being true, if I did not drink too much diet soda, therefore I can sleep. Well, that's not necessarily the case. Maybe not drinking the diet soda, but something happened that day that they still got a headache regardless. It was a different reason. Maybe they got hit in the head with something and therefore they can't sleep. Or even if they don't have a headache, maybe they can't sleep for some other reason. So, it's not a valid argument based off of the laws of logic. So, it's, not a valid argument to be made here. Now, for situations like these, now I gave you like equations to do where you're converting from one base to another base, and neither one of them are base 10. Chances are most questions that would be presented to you, um, you know, would possibly have you just, go from, one base to base 10 or base 10 to another base. Um, this one here has you practicing both skills though. So, I want to make sure that, you can do both of them. So that's why these questions will, sometimes be shown on a test, because it shows that you can convert something from one base to base 10 and then from base 10 to another base. And that's the way you have to handle these problems. So basically the way we're going to handle this first problem is that I'm going to go from, something base 15 to something base 10, and then I'm going to go from that new thing base 10, and I'm going to make that something base 6. And that's the best way to do it. If you try to go directly from base 15 to base 6, that could cause you some difficulty because we're used to working in base 10 math as it is. So even doing the converting and computations could be problematic as it is. Trying to go from one base that you're unfamiliar with and don't work with regularly to another one that would just be making things much more difficult. So I'm going to take care of this one first. I'm going to go from base 15 to base 10. Now, in base 15 math, I mean, the B, E, and D represent digits. Digits that are equivalent to values that for our base 10 math would be essentially, double digit numbers. So, when I'm dealing with anything over base 10, if I see the letter A, that usually represents a value of 10. B represents a value of 11. C represents a value of 12. D would represent a value of 13. And E would represent a value of 14. And I need to keep those straight because those are the numbers I need to make use of when I convert to base 10. Because when I look at this here, I have my 15, I have my unit position, my 15s to the first. This is my 15 squared. This is my 15 cubed position. This is my 15 to the fourth position. And what's in those places are the numbers I would need to multiply to that power of 15. So, BED 1/8 to sub 15 is going to be essentially, I'm going to have 11 times 15 to the fourth plus E would be 14 times 15 cubed plus D, which represents a 13, times 15 squared plus 1 times 15, and the units position is just going to be an 8. So I would work out that problem first, and this gives me 607,073 in base 10. Now I want to convert this to base 6. So I have to be aware of my powers of 6. I have to be aware, okay, well, 6 squared is 36. 6 cubed is 216. I want to see, like, how high up I have to go, because I have 607,073. I mean, obviously 216 would probably go into this more than 6 times, so I want to make sure I have, all the powers of 6 I could use to help me figure this out. 6 to the 4th is 1296. 6 to the 5th is 7776. 6 to the 6th is 46656. 6 to the 7th is 279936. And that's the highest power of 6 that can go, that will actually go into 607073. Because if I do 6 to the 8th power, I end up with 1,679,660. So that's way over. So the first number I'm going to divide this into, or divide into this, is the 6 to the 7th power. And so I basically do that division, 607073 divided by 279936, and I find out that this is equal to 2 times 6 to the 7th plus 47,201. I now take this remainder, the 47,201, and I took care of this one. We'll see how many times that 6 to the 6 goes in there. Well, I can tell just by the fact that they're very close together, it's going to go in once. So that equals 1 times 6 to the 6th plus 545. Now I take this and come over here. Well, 6 to the 5th is not going to go into that, so it's much bigger. So I'm going to say 0 times 6 to the 5th plus that 545 again. 1296 is also too big, so I'm going to have a 0 times 6 to the 4th plus 545. Now 6 cubed, I can say, well, 6 cubed I find goes in twice. So I'm going to have 2 times 6 cubed. And if I divide 545 by 216, I get 2 with the remainder of 113. So I bring that remainder down here. I now divide by the 6 squared. So 36, goes into this 3 times. I'm left with a remainder of 5. So the 5 would go here. I would next try to do whatever goes in by 6 to the first power, but none of those would work. And this 5 would be the remainder. It's the unit thing. So basically the number I'm looking for is this number right here. So that's going to be 21002305 to the 6th power. So that's how you would do that one. And it works either way, depending, if you're going from higher base to lower base, or lower base to higher base, you're still going to go from the one you have all the digits for, to base 10, and then from base 10 to the one that you're looking for, whatever base you're looking for. So let's try to do that again with part B. 7413, sub 8, which means, this is the number in base 8. So when I look at this, again, I'm going to do the conversion to base 10. Here we go. 7413 base 8 indicates, well, so again, this is my units, this is my 8 to the 1st, this is my 8 squared, This is my 8 cubed. So I have 7 times 8 cubed plus 4 times 8 squared plus 1 times 8 to the first, or 8, plus 3. And that ends up being 3851, base 10. Usually I don't have to put the base 10 under there, but just for the sake of argument. Now I want to be aware of my powers of 11. So I have my 11 to the first power, which is 11. I got my 11 squared, which is 121. I have my 11 cubed, which is 1331. I have my 11 to the fourth, which actually goes higher than 3851. It's actually 14,641. So that's not going to go into 3851. So I'm going to start with the 3851. I'm going to see how many times 11 cubed goes into it. And basically, 1,331 goes into this twice. So I'm going to have 2 times 11 cubed. And I'll have a remainder left over of 1189. So that takes care of this one. And now I'm going to take the 1189 and see how many times 121 goes into it. It goes in 9 times. So 9 times 11 squared, and it leaves me with the remainder of 100. So now I have the 100 over here. And I'll go with 11. How many times does 11 go into 100? Well, it goes in 9 times. 9 times 11 is 99, so I have a remainder of 1. And this 1 just kind of drops down to here. So the final answer would be this number right here. So checking here. Okay, yeah. 2991, base 11. So and the easiest way to check this out is just go back and say, okay, if I do, this is my units. This is my 11 to the first, 11 to the second, 11 to the third. Does that come out to be the 3851 again? That 7413 to the eighth was in base 10, and that would be, a way to check it. So that is the end of this first part of this review. These 9 problems took a bit of time, so I want to make sure that you have smaller portions to go through. So the next video is going to start on with number 10 and move beyond that. So make sure you look at that video for any of the help you need on those problems. I'll see you there.